So in the previous class we were solving problem number 9. Half of the problem was completed. We'll finish it. I'll just glance the things which I covered in the previous class in this particular problem. A cantilever portion of a pre-stressed concrete bridge with a rectangular cross section 600 mm wide and 1650 mm deep. Cross section is given, 8 meter long. Length of the beam is given, and the support condition is cantilever. Okay. In previous problems, in all previous problems, it was a simply supported beam, but here in this problem, it is a cantilever beam. Okay. Carries a reaction of 350 kilonewton from the suspended span together with a uniformly distributed load of 60 kilonewton per meter inclusive of its own weight. These are the loading condition I have written in the figure. The beam is pre-stressed by 7 cables, each carrying a force of 1000 kilonewton. There are 7 number of cables, each carrying 1000 kilonewton. And the screen is not visible, right? I forgot to share the screen. Just a minute. Screen is visible, students? Students? Screen is visible?
Yes,
Please.
sir.
Okay. 7 cables, each carrying a force of 1000 kilonewton. There are 7 number of cables, and all the 7 cables are placed at different locations. Means 3 cables are placed at 150 mm from the top of the beam, and 3 cables are placed at 400 mm from the top, and remaining 1 cable is placed at a distance of 750 mm from the top. That is mentioned in the problem. And it is asked to calculate the principal stresses at a point 550 mm from the top of cantilever at support section. Okay, that is the question. So as the bars given are at different locations, okay, they are not in a single line. All the 7 bars, they are not in a single line. 3 bars are at 150 and 3 bars at 400 and 1 bar at 750 mm. First we need to locate the centroid for these bars. Okay, that we have already done. Okay, from the top we have located the centroid of these bars, means centroid of pre-stressing force carried by these bars. That we got it as 343 mm. Okay, 343 mm we got, that I have mentioned in the figure. After that we have calculated the eccentricity. Eccentricity is the distance between the centroid of the cables to that of centroid of the whole figure. That we have calculated. Okay, the total depth of the beam given is 1650 mm divided by 2 will give distance of centroid from the top fiber, that is 825, minus 343 will give, if you do, you will get eccentricity. Okay, means distance between the centroid of the bars to the top centroid of the figure. Okay, eccentricity we have calculated, and in the problem it is said that there are 7 cables, each carrying a force of 1000 kilonewton. Okay, so each cable is carrying 1000 kilonewton. For 7 cables, the total pre-stressing force we have calculated, that is 7000 kilonewton or 7000 into 10 power 3 Newton. Okay. Now, just a minute. Yes. Now, moment due to pre-stressing force. Now, what we will do is we will calculate we will write the equation first. Okay, we will write the equations for the principal stresses. Write the equation. Now all the required parameters we have calculated. It is asked to find principal stresses at a distance 550 mm from the top of cantilever beam. Correct? Now below write the formula. Principal stresses formula we already know. principal stresses at 550 mm from top at support section. Okay, that we will find. You write the figure of a cross section so that it becomes easy for doing the calculation. Write the figure of a rectangular section, you write. The total depth is given as 1650. We need to find the principal stresses at a distance 550 mm from the top. Okay, 550 mm from the top. From the top. Total or overall depth is 1650. Okay, now write the formula of principal stresses. We know that principal stresses sigma max or sigma minimum is equal to fx plus fy divided by 2 plus or minus half of root of fx minus fy whole square plus 4 tau v square is the formula. Now you find one by one. First we will find fx. Okay, first we will find fx. Here this is very important steps, students, listen. See, the type of beam given is a cantilever beam here. Okay, the type of beam given is a cantilever beam. For simply supported beam, what is the moment it supports? If it is a simply supported beam, what is the moment at support? Tell me. What will be the moment at support if it is a simply supported beam?
0.
It will be 0. Okay, it will be 0. And if you refer to the previous problems, okay, if you refer to the previous problems, in most of the in almost all the problems, the type of cable given was parabolic, and particularly it is mentioned that it has some eccentricity at the midspan and zero eccentricity at the support. Okay, eccentricity at the support is 0 in almost all the previous problems. Okay, in almost all the previous problems, the support condition was simply supported where moment equal to 0 and eccentricity equal to 0. But in this particular problem, what is the type of support given? It is a cantilever support. For cantilever support, at the support there exists the moment. Okay, the moment is existing. Even if you take the eccentricity also existing, because whatever the cables provided here, they are straight cables. Okay, at along the length of the beam, throughout the length of the beam, the cables have got eccentricity of how much? 482 mm. Therefore, the fx, the formula for fx will be, you just refer to the model number 1. Just a minute. Okay, fx should be determined by considering that eccentricity at the support as well as moment at the support. Okay, moment at the support. Okay, referring this, we need to formulate the equation for fx. Okay, referring this basic principle of pre-stressed concrete, we need to formulate the equation for fx. Now, the type of beam given is a cantilever beam. Type of beam given is a cantilever beam. For cantilever beam, what will be the bending pattern? What will be the bending pattern? Like this, correct? Like this, it will be a the bending pattern will be there. Means the top fiber will be subjected to the tension, bottom fiber will be subjected to the compression. But in case of simply supported beam, it is reverse. In case of simply supported beam, it will be reverse. Okay, top fiber compression, bottom fiber tension. And whatever the formula given here in module 1, this is with respect to simply supported beam. Okay, top compression is considered, bottom tension is considered. Okay, and formula, the respective formulas are formulated. Okay, now to formulate the equation for fx here, we need to take both moment at the support, okay, both moment at the support as well as eccentricity at the support. But for this particular problem, moment is also there, eccentricity also there. So the formula for fx becomes top fiber tension, no? Top fiber tension. So refer the tension case here in the problem number 1. What is the tension case? So bottom tension is the, no, you refer these things and formulate the equation, that is P by A plus PE by Z minus mg by Z minus mq by Z. Okay, that you write here P by A fx equal to P by A then plus P by ZB minus mg by ZB minus mq by ZB plus PE by ZB minus mg by ZB minus mq by ZB. Okay, have you understood, students? Here the type of beam given is a cantilever beam. For cantilever beam, at supports moment also exists, eccentricity also exists. Therefore, formula for fx will be this much. If moment and eccentricity is 0, this whole all these three terms become 0. Only we will get P by A. That we practiced in solving previous problems. In all previous problems, the simple support and 0 eccentricity was given. It was just P by A. Okay, is that clear for you all, students? Is that clear, students? Any doubts here? Any doubts?
No, sir.
Okay. Now we will find all these parameters and we will substitute. Okay, we will find all these parameters and we will substitute. Now, and one more thing, it is asked to calculate magnitude of principal stresses at a point 550 mm from the top. Okay, Okay, now whatever the parameters we are finding with respect to the depth of 550 mm only we need to find. Okay, with respect to depth of 550 mm only we have to find. Therefore, here Fx equal to P by A plus PE by Z. PE by Z is 0. That I will write it as I by Y. Okay, I will rewrite that equation and minus here it is said that in the problem uniformly distributed load 60 kilonewton per meter inclusive of its own weight. Inclusive of its own weight means it is mg plus mq. Okay, if you find the moment you will get the value of moment due to dead load plus moment due to live load divided by z. Z I will write it as I by Y. I by Y. I by Y. Okay. Now whatever the load given, live load given, it is inclusive of dead weight. That is why. So it is, if you find the moment due to that UDL, you will get inclusive the moment due to dead load plus live load. Inclusive of dead load only, you will get the moment. That is why I have merged these two equations. And for Z, I have written as I by Y. Okay. Now, in another step, I will rewrite the equation, the final equation Fx equal to P by A plus I you take to the numerator PE into Y divided by I minus mg plus mq. I will consider it as m whole divided by I by Y. Okay, moment inclusive of dead load moment. Okay, now the pre-stressing force P is known, then area of cross section is known. You find one by one. Pre-stressing force P is equal to, just we have calculated, there are 7 cables carrying 1000 kilonewton each. 7000 kilonewton is the pre-stressing force, that you write it 7000 into 10 power 3 Newton. Then area of cross section is the width is 600 and depth is 1650. 600 into 1650 is the area. Then eccentricity, you have determined eccentricity how much we got eccentricity. It is 482 mm, correct? Eccentricity is 482 mm. E is equal to 482 mm. Then Y, okay, Y is the distance of centroid from the reference axis. Means here it is asked to find principal stresses at a distance of 550 mm from the top. Therefore, the Y bar distance of centroid becomes how much? It is Y is equal to 550 divided by 2 is equal to 275 mm. Okay, below you write the same calculation. Y is equal to 550 divided by 2 is equal to 275 mm. Refer figure. Okay, then moment we can find it. Okay, to find moment, inclusive of dead load. Okay, just copy the loading condition. Intensity of UDL is 60 kilonewton per meter. 60 kilonewton per meter, and point load at the end of the beam, that is 350 kilonewton. 350 kilonewton. And here don't get confused. It is said that say 8 meter long and carries a reaction of 350 kilonewton from the suspended span at the free end. Okay, he said it has a reaction. Don't get confused. It is the load only. It is load only means you understand there is some element. Okay, there is some element resting over the edge of the beam. Due to that element, that reactive force is again transferred to the end of the beam. And don't take in upward direction that reaction. Okay, it is not the thing that don't get confused with the reaction. It is load only. Okay, it is load only, load which is acting at the end only. Okay, 350 kilonewton. The span of the beam is given as 8 meter. Span of the beam is given as 8 meter. Now you can find moment, right? Moment at the support. Okay, we are finding principal stresses at the support at a distance of 550 mm from the top fiber. You find moment at support. Therefore moment at support is equal to m is equal to moment of this point load about the support is 350 into 8 meter. Then moment of 60 kilonewton meter about the support, UDL, moment of UDL about the support. First you convert that UDL into point load, that is 60 multiplied by 8 meter into perpendicular distance, span divided by 2, 8 divided by 2. By this we will get the total moment acting on the acting at the support. How much? Tell me the answer. Calculate, students. Tell me the answer quickly. What's the answer?
$4720 kilonewton per meter, sir.
Yes, 4720 kilonewton meter. Okay, in terms of Newton millimeter, m is equal to 4720 into 10 power 6 Newton millimeter. Okay, now all the required parameters are known. Just find fx now. Fx equal to therefore fx equal to p by a. P is 7000 kilonewton. 7000 into 10 power 3 divided by area is 600 by 1650. 600 by 1650. Then PE into y divided by I plus P is 7000 into 10 power 3 into eccentricity 275 into y. Sorry, eccentricity is 482. Eccentricity is 482 into y bar 275 PE y bar divided by moment of inertia. Moment of inertia we did not find. No, you find it. Moment of inertia is equal to I equal to BDQ by 12, 600 into 1650 cube divided by 12. What is the value of moment of inertia? Tell me.
224.6 into 10 to the power 9
Yes.
mm per power 4.
4.6 into 10 power 9 mm4. Okay. So 224.6 into 10 power 9 minus m by I by y. Okay, y again you take to the numerator only. Moment we know, that is 4720 into 10 power 6 into y value is 275 divided by moment of inertia 224.6 into 10 power 9. Tell me the answer. Arjun, tell me the answer. Asha, Darshita, tell me the answer. Kruti, Kirti.
Sir, 5.42 Newton per mm square.
Yes, 5.42 Newton per mm square. Correct. Okay. Then now we got fx. Fx we got. Fy will be 0. There is no vertical pre-stressing steel given. Fy equal to 0. The directly right Fy equal to 0. Okay. Then what else we need to calculate? We need to calculate tau v, that is shear stress. We have the formula for shear stress. Write it. And tau v is equal to, what is the formula? Vu into Ay bar divided by Ib is the formula. Okay. And Vu is equal to shear force at support is equal to, you just calculate the shear force, add these two loadings 350 plus 60 into 8, 350 plus 60 into 8, how much you'll get? Answer
830.
830, sir.
yes, 830 kilonewton, nothing but 830 into 10 power 3 Newton. Okay, Vu we got, and Ay bar, I think it is, yeah, we have to calculate it. Ay bar we have to calculate. Area, how much here? Shaded portion 550 into this width is 600 mm. And y bar will be 550 divided by 2, 275. Ay bar is equal to, area is 600 by 550 into y bar half of 550, that is 550 divided by 2. How much will get Ay bar value? Refer figure.
19.75 into 10 to the power 6 mm cube, sir.
Yes, 90.75 into 10 power 6 mm cube. Okay. Then moment of inertia is known, width of beam is known, just substitute, you will get tau v. Therefore tau v is equal to Vu is 830 into 10 power 3 into AY bar 90.75 into 10 power 6 all divided by moment of inertia 224.6 into 10 power 9 224.6 into 10 power 9 into 600 is the width of beam. How much shear stress?
So 0.558 Newton per mm square.
Okay, 0.558 Newton per mm square. Now, I think all the parameters required to calculate principal stresses are known. Just substitute and get the answer. Sigma max is equal to, therefore, sigma max is equal to fx plus fy divided by 2. Fx is 5.42 plus 0 divided by 2. 5.42 plus 0 whole divided by 2 plus half of root 5.42 minus 0 whole square plus 4 tau v square into 0.558 square.
.734.
Okay, 5.734 Newton per mm square. And sigma minimum is equal to 5.42 plus 0 whole divided by 2 minus half 5.42 minus 0 whole square plus 4 into 0.558 square. What is the answer? Sigma minimum? Sir, sigma minimum how much?
So minus 0.055 Newton per mm square.
Yes. Minus 0.055 Newton per mm square. Okay. So this completes the problem. Okay. If you have got any doubt still, you can ask. Okay. To this, the analysis problems are over in module 4. Next is design problems. Okay. Till now, what you have learnt is you have learnt how to do the analysis for shear stresses, okay, or the principal stresses in a pre-stressed concrete beam. Next, you will be learning how to design a beam for a shear force. Okay, how to design a pre-stressed concrete beam for a given shear force. Okay, that is the next part. And they are also very simple problems and simple procedure. Okay, the formulae are given in the code book. Just refer as like IS 456 in IS 1343. The guidelines are given to design a PSC beam for shear, and referring to those guidelines, we have to perform the design. That's it. Okay, very simple problems. Very simple problems. Okay, as like analysis problems. And I just noted the various design steps involved for a shear design of PSC beam. First, initially we have to calculate the design shear force, means factored shear force we need to calculate. Okay, PSC beam with some shear force will, for that we need to calculate the design shear force. Means we have to calculate factored shear force by multiplying by 1.5. Okay, then next step is to calculate the ultimate shear resistance. Ultimate shear resistance. If you take any beam, okay, any PSC beam, it has got some resistance to the shear. Okay, even if you are not providing any shear reinforcement, it has got some resistance, right, for the shear. That resistance we need to find. That is termed as VC naught. Okay, that is termed as VC naught. The formula for that VC naught is given in the code book itself. Okay, formula for that VC naught is given in the code book itself. That is page number 46. Let me show that. Yes, here we have the formula. The ultimate shear resistance of a section uncracked in flexure. Okay, ultimate shear resistance VC naught is given by 0.67 B into D root of FT square plus 0.8 FCP FT, where B is width of the member. If it is a flexure section, we need to calculate. We need to take width of web or the BW. Okay, and D is the overall depth of the member, and Ft is the maximum principal stress. Okay, maximum principal stress. Sometimes this Ft value will be directly given in the problem. If it is not given, FCK will be given. Okay, FCK will be given. Using that FCK, you can calculate Ft by using this formula. That is using 0.2 for root of FCK, you will get Ft. And FCP is the compressive stress at central axis due to pre-stress. Okay, that we can calculate. Pre-stressing force will be given, area of the section will be given, P by A if you do, you will get FCP. Okay. B 8 semester. Okay, FCP, this value will also be most of the times FCP will be directly given. Okay, if not given, we can calculate. Okay, using all these formula, we will calculate VC naught. Okay, the shear resistance of the member we will calculate. Okay, shear resistance of the member we will calculate. Now, after calculating shear resistance, let me go to the notes. Okay, after calculating shear resistance, then that shear resistance will be compared with the actual shear force that is acting on the beam. Okay, the actual shear force acting on the beam. Okay, VC naught is the shear force that can be handled by the PSC beam. Okay, means ultimate shear resistance. Okay, this shear resistance will be compared with the actual shear force that is acting on the section. Okay, if the shear resistance of the beam is less than, okay, if the shear resistance of the beam is less than that the shear force acting on the beam, then we have to design the beam for shear. Understood? First we will calculate what is the shear resistance of the beam, then that shear resistance will be compared with the actual shear force that is acting on the beam. If the shear resistance of the beam is less than that shear force acting on the beam, then we have to perform the design for shear. Okay, for the rest of the shear force VU minus VC naught shear force, we need to perform the design. We need to give extra shear reinforcement. Okay, if VC naught means the shear resistance of the beam is greater than that shear force acting on the beam, then we have to provide a minimal shear reinforcement. Okay, very minimum shear reinforcement as per the code book IS 1343. This formula is also given in page number 48. Okay, I will show you. Okay, using this formula. Okay, using this formula, minimum shear reinforcement. Okay, as we in case of doubly reinforced beam, as we give a minimum in case of singly reinforced beam, we will give minimum 2 bars at the top, right? Even if it is not required. Like that, we have to provide some minimum reinforcement using this formula. Okay, we have to select some stirrups, whether it is two-legged or the four-legged stirrups. We have to select. Fi, the grade of the steel will be known. Okay, and the area of steel we can calculate by assuming the two-legged or four-legged stirrups. B means width of the beam will be known. By that, we can calculate the spacing. Okay. For the first case, means for if the VC naught is less than VU, we have to utilize this formula. We have to utilize this formula, okay, to find the spacing of the stirrups. Okay, this is what the procedure we need to follow for design for shear in a PSC beam. And whatever the spacing we have calculated now using this formula. Okay, that spacing should not be greater than these two values, that is 0.75 dt and 4 dt is the effective depth. Okay, dt is the effective depth, or 4 bw. Okay, 4 times width of the web or width of the beam. Okay, this guideline is also given in class number 22.4.3.2 in the page number 48. Okay, here it is given, you can go through it. Okay, you can go through it. So this is what the procedure we have to follow for design of PSC beam for shear. Did you got some idea, students? Did you got some idea on design for shear?
Yes, sir.
Okay. So when we start solving problem, then you will get the clear idea. Okay, you will get the clear idea. We will solve a design problem now. First problem you write. Okay, you write first problem and try to solve by your own. Okay, I got a few minutes meeting. Okay, I'll just attend the meeting and I'll join back in very few minutes. Okay, you keep solving that problem, you try yourself. Okay, I have explained the procedure. Okay, I explained the procedure. You just open the soft copy of the code book, and what are the procedure I have explained now, that you follow. Try to design by your own. Okay, I'll join back in very few. Write the problem and keep solving. I'll join back. Okay. Okay, friends. So we'll solve the problem. Anyone started solving? Anyone started solving the problem? Okay. So whatever the procedure I have explained now, that procedure we will follow and we will design. Okay. You just go through the problem. The support section. The support section of a PSC beam 150 by 300 is to resist a shear of 100 kilonewton. Okay. The pre-stress at centroidal axis is given 5 Newton per mm square. Pre-stress at centroidal axis means what? It is FCP. Okay, that formula I have shown now. FCP value. FCK is given 40 Newton per mm square. The cover to tension reinforcement is given. That cover is given. Check the section for shear and design suitable shear reinforcement. And FT is also given 1.5 Newton per mm square. Okay, write the cross section of the beam. Okay. The cover is given. Cover is given as how much it is? 45 mm. 45 mm is the cover. And overall depth of the beam, capital D, is equal to 300 mm. Okay, 300 mm. Therefore, the effective depth dt will be equal to 300 minus 45. How much will get? 255 mm. Okay, effective depth. So the notation is taken as dt in that formula. That's why I will take the same notation, dt, effective depth. Okay, B is 150 mm. So B is equal to 150 mm. Overall depth is equal to 300 mm. Effective depth is equal to dt is equal to 300 divided by 2. Sorry. dt is equal to 300 minus 45 is equal to 255 mm. Okay, 255 mm. Then pre-stress at centroidal axis is given as 5 Newton per mm square. That is pre-stress at centroidal axis. Centroidal axis is equal to FCP is equal to 5 Newton per mm square. Then FCK is given 40 Newton per mm square. FT is given tension stress 1.5 Newton per mm square. Okay. Now we will follow the steps. What is the first step? We need to find VC naught first. Okay, we need to find VC naught. Before that, you find the factored shear force. External shear force. External shear force. The shear force given has how much it is given? 100 kilonewton. Therefore, the factored shear force is equal to. Therefore, the factored shear force or the ultimate shear force. ultimate shear force is equal to 100 into 1.5 is equal to 150 kilonewton. Okay, ultimate shear force. This you call it as V, and ultimate shear force as VU. Okay, ultimate shear force is equal to VU is equal to 150 kilonewton. Next, you calculate internal shear resistance using that formula, which is given in page number 46. Internal shear resistance VC naught I'll go to the code book, page number 46. 0.67 B into capital T root of FT square plus 0.8 FCP into FT. Okay, VC naught is equal to that is internal shear resistance is equal to 0.67 B into capital D root of FT square plus 0.8 FCP into FT. Okay, which is given in page number 46 IS 1343 1980. Okay, B is known, B equal to 150 width of beam and overall depth of the beam. Overall depth of the beam is 300 mm. FT is known, FT is equal to 1.5. FCP is equal to 5. Therefore, VC naught is equal to 0.67 into 150 into 300 root of 1.5 square plus 0.8 into FCP 5 into FT 1.5. So what is the shear resistance? Tell me.
86.59.
Yes, 86.59 into 10 power 3 Newton, or VC naught is equal to 86.59 kilonewton. Okay. Now this is the internal shear resistance. Okay, the beam is capable to carry a shear force of 86.59, but the actual shear force, ultimate shear force acting on the beam is 150 kilonewton. When you compare both, the shear resistance is less than that shear force acting on the beam. Then beam requires the shear design. Okay, below you write comparing. This is greater than VU, that is 150 kilonewton. Comparing VC naught is greater than VU, therefore provide shear reinforcement. Okay, just a minute students, I will be back. So comparing both VC naught and VU, the shear resistance is the less than the shear force that is acting on the beam. Therefore, shear reinforcement has to be provided. This is less than symbol, no? Which is less than that shear force which is acting on the beam. Hence, it requires the shear reinforcement. Okay, it requires the shear reinforcement. Now, in the next step, what we have to do? We have to assume some stirrups. Either it may be 2-leg stirrups or 4-leg stirrups, and you have to find the spacing for the stirrups. Okay. Now, in the next step, step C. Design of shear reinforcement. Design of shear reinforcement. Therefore, you can assume 2-legged diameter stirrups using 2-legged. Usually the stirrups diameter will be taken as 8 mm or 6 mm. I'll take 8 mm. 2-legged 8 mm dia vertical stirrups. 2-legged 8 mm dia vertical stirrups. Therefore, you find the area of vertical stirrups. SV represents vertical stirrups. Okay. ASP is equal to pi d square by 4 into 2. How much will you get area of stirrups? This is 2-leg, no? That is why multiplied by 2. What is the answer? Tell me the answer, students.
The 100.53.
Yes, 100.53 mm square. Okay. Now we have decided 2-legged 8 mm dia vertical stirrups. We have to find spacing for the same. At what spacing these stirrups should be provided to handle that shear force which is acting on the beam. Okay. You write the side line as spacing. Write the side line as spacing. Okay. Now for spacing, you need to calculate spacing in 4 different ways. Okay. Remember, you need to calculate spacing in 4 different ways. Whatever the minimum spacing out of all the calculations now, that spacing you need to choose as spacing of the stirrups. Those 4 calculations are there in the codebook itself. Okay. They are there in the codebook itself. Okay. Using this formula, you will get 1 SV. Using this formula, okay, for minimum shear reinforcement, you will get 1 SV. Then 0.75 dt. If you calculate, you will get one particular spacing, and 4 times web thickness for flanged members. Okay, 4 times B. If you do, you will get one particular spacing. So all these 4 calculations you do, whichever the minimum spacing value you get, that you choose as actual spacing for the stirrups. Okay. So first one, Most of the times, if VC is less than V, most of the times you will get lesser spacing for this case only. First use this formula, ASV by SV is equal to ASV by SV is equal to V minus VC divided by 0.87 Fi dt. V minus VC divided by 0.87 Fi dt. V minus VC represents what? This is the actual shear resisting capacity. This is the shear force acting on the beam. For rest of the shear force means 150 minus 86.59, you are designing the shear reinforcement. That is why it is taken as V minus VC. Okay. You write the page number here. Page number 48. IS 1343 1980. Okay. ASV we have calculated, that is, this is VU. Okay. ASV we have calculated, it is 100.53 divided by SV is equal to VU minus VC. VU is 150 kilonewton, that is 150 into 10 power 3 minus VC naught, 86.59 into 10 power 3, 86.59 into 10 power 3. You need to substitute in terms of Newton because Fi will be in terms of Newton per mm square. Whole divided by 0.87 Fi. How much it is given? Fi not given, no? Grade of steel. We will assume 415 if it is not given. Okay. Into 415. What is the spacing we will get?
145.9.
Fi into dt I forgot. Sorry. Dt is means effective depth. It was 255 into 255. What is the answer you told? 140?
145.96.
Yes. 145.96 mm. Okay. Then second calculation using another formula for minimum spacing, that you use that formula. ASP by BSP is equal to 0.4 divided by 0.87 Fi. ASP divided by BSV is equal to 0.4 divided by 0.87 Fi. ASV is 100.53. B width of beam 150 into spacing we need to calculate 0.4 divided by 0.87 into 415. What is the spacing? Tell me by this calculation.
604.9.
Yes. 604.9 means we can take 605 mm. Okay. Two calculations are over. Two more calculations are there. Third calculation 0.SV is equal to 0.75 times the effective depth. This is given in page number 48 only. You just refer to the theory part which I shown. SV is equal to 0.75, effective depth is 255. Answer?
$191.25.
191.25 mm. And fourth calculation for spacing, 4 into SV is equal to, he said that 4 times width of web in the theory of that page number 48. Okay, 4 times the web thickness of fringed members, he said. But here we have the rectangular section, so width of rectangle we have to take 4 into B. 4 into B. 4 into 150 is equal to 600 mm. Okay. Like this, we have to calculate the spacing by 4 different calculations. Okay. Then, whichever the minimum spacing out of all these calculations, that spacing we have to give for shear reinforcement. Okay, which is the minimum value? 145.96, 605, 191, 600. So 145.96 is the minimum value. We will provide this spacing. Okay. Therefore, at the last you write, therefore, taking the least value of above calculations that is 145.96 145.96 mm. Provide two-legged 8 mm dia stirrups at 145.0. You can provide at 140 mm. 140 mm center to center. Okay. Therefore, two-legged 8 mm dia vertical stirrups at 140 mm center to center. Okay. This completes the design, and you need to give detailing also, reinforcement detailing also. You write the figure. As for reinforcement detailing, these are the main bars. Okay, these are the main bars. The details of the main bars are not given. Just we will take two sets of bars at top and bottom. Okay, no need to worry about the main longitudinal bars. Here we are doing design for the shear. Okay, at the support you give stirrups at 140 mm center, and at the mid span, okay, means at 1/3 of the span, you can slightly increase the spacing. You can slightly increase the spacing. Okay. Because at the middle third span, the shear force will be less only. Okay, at the support it increases. Here it is. What is center? Okay. At the middle third span, you can provide the second lowest value. Second lowest value is which one here? 145, 605, 191 is there now. That you can take 190. Okay. Two-legged 8 mm at 190 center to center. Okay, because if you look into the shear force diagram for beam, what will be the nature of shear force diagram? At the support it will be higher, at the center of the span it will be 0. So like this you will get the shear force distribution, or the shear force diagram. Therefore here corresponding to this zone, you can provide a less number of you can increase the spacing. Okay, you can increase the spacing. Okay, 190 center to center, and here 140 center to center, because the shear force is here at the support sections. 140 center to center. That is why we will slightly increase the spacing at the midspan. Okay. Here it will be, shear force will be equal to 150 kilonewton. Ultimate shear force. Gradually it will reduce us to 0 at the midspan. That is why we will slightly increase the spacing. Okay. You can write the cross section. Main bars, you take 4 main bars. And give the stirrups. Okay. Two-legged 8 mm vertical stirrups. 150 and 300. So this completes the design problem. Very simple. Okay, very simple procedure. You can easily solve this design. You can easily perform the design. Any doubts in this problem, students? Any doubts? I hope it is clear for everyone. Shall we move on to the next problem then? Okay.
Repeat once.
Yes, yes. Still writing the detailing.
Yes, sir.
Okay. We will move to the next one. No need to write this shear force distribution. For your understanding, I have written. Okay, in the examination, if you write this much detailing, it is enough. Okay. Write the second problem. Write the second problem. Take 2 minutes time. Okay. Next problem. Write the figure as well. Write the figure as well. A parabolic cable is given in the problem. I think this month 19th you have third internals, right? When is your third internal?
Sir, when will be
19th.
our final exam, sir? Final exam, sir.
I think it is not yet mentioned from the university. Shortly they may leave the timetable.
Sir, offline class start ಮಾಡ್ತೀರಾ sir?
Yes.
Sir, offline class start ಮಾಡ್ತೀರಾ?
That guideline still we have not received. Maybe online only it may run. See, if anyone of you are not vaccinated, please get the vaccination as soon as possible. Okay. There may be a rule that only the vaccinated students are allowed to write the examination like that. Something like that it is there. So please get vaccinated. Okay. That is why from the college, from the institution, they have started the vaccination drive. I think most of you are already vaccinated for the first dose. Okay. You go through the problem. It is a slight different problem compared to the previous one. A PSC beam 250 mm wide and 1500 mm deep is subjected to a shear force of 900 kilonewton. The shear force given is 900 kilonewton. Cross section of the beam is given, that is written. Okay. The fiber stress under working loads is equal to 4 Newton per mm square. Let me write the given data. B is equal to 250 mm and overall depth is equal to 1500 mm. Then the fiber stress under working loads is equal to 4 Newton per mm. Fiber stress means FCP here. Fiber stress FCP is equal to 4 Newton per mm square. The effective pre-stress is given as 1000 Newton per mm square. Area of cable is given, pre-stress is given, area of cable given. You can find the pre-stressing force, right? Area of cable is equal to 1500 Newton per mm square. Okay. Then what else is given? Design the shear reinforcement, and it is said that the cable are inclined at an angle of sine inverse of 1 by 6. Okay, inclination of the cable given, the slope of the cable at the support, it is sine inverse of 1 by 6. Okay. Write the vertical component of the pre-stressing force as well, that is required for the calculations. I will tell you. Here in the problem, the overall depth is given, but cover not given. Cover is not given. If cover is not given, you need to assume some cover. Okay, assume some cover. How to assume means you just look into the overall depth of the beam. Just by looking into the overall depth, you choose some cover. Okay, here 1500 mm depth is there. For 1500 mm, you can go for 100 mm cover. If it is a 500 mm overall depth, you can go for 50 mm cover, like that. Okay. If cover is not given, you have to assume. In case of design problems, no, few parameters will not be given. If any parameter or if any data required is not given, you need to assume and you need to perform the design. Okay. Now, assuming cover of 100 mm, effective depth is equal to dt is equal to overall depth is 1500 minus 100, 1400 mm. Okay. Now you follow the procedure. First you calculate the external shear force. Step 1, external shear force. External shear force V is given as 900 kilonewton. Shear force is equal to V is equal to 900 kilonewton. Force